Find each limit. If it exists, show the work where starred. So we have limit as x goes to 0 of sine of 6x over 42x. The first thing your eye should be attracted to is this 42 in the denominator. We can factor that out, and we are left with 1 over 42 times the limit as x goes to 0 of sine of 6x. That's supposed to be a 0. Sine of 6x over x. And one thing that we proved numerically, and we can also prove this trigonometrically, but the limit as x goes to 0 of sine kx over x is just equal to k. So that's a fact. And see how it's boxed like that? That means it's important. Okay, so we have 1 over 42 times this limit, which we just said is 6. 1 over 42 times 6, so we're left, just those cancel, and we're left with 1/7. Don't put that into a decimal. Just leave it as a fraction. I'm going to erase this because we need this space later. The limit of as x goes to 1 of 3x squared plus 5 over x plus 2. Well, there's no problem with evaluating this expression right here at x equals 1, so we can just use substitution. So this is equal to 3 times 1 squared plus 5 over 1 plus 2, or 8 over 3, 8/3. The limit as x goes to 3 of x squared minus 9 over x minus 3. Well, we have a problem here. We can't just we can't evaluate this expression right here at x equals 3 because we would divide by 0. So we can say, we can look at this algebraically. The limit as x goes to 3. This is x squared minus 9 right there is a difference of squares. So we have x minus 3 times x plus 3, and that's over x minus 3. Now we get to use our red and cancel those two factors, and now we can use substitution in this expression. So the answer is 6. So the limit as x goes to infinity of 3x squared plus x minus 2 over 4x to the x cubed minus x squared minus x plus 1. The dominant power here as x gets large is the power of this x right here cubed, so this answer is 0. We can almost we like to say we can almost ignore these terms, these other terms here, x and minus 2, and the denominator x squared and minus x squared. I think that's a plus x squared minus x plus 1. We can almost ignore those because as x gets large enough, these two terms, 3x squared and 4x cubed, dominate the expression. Okay, so one quick note about this. Don't forget some of your factoring. If you see a difference of cubes, so a cubed minus b cubed, let's not forget that this is a minus b times a squared plus, is it 2ab? I have to remember. No, it's a. It's minus ab. All over the place here. Bear with me. It's oh, and then it's all plus. Sorry. So this is a plus ab plus b squared, right? So this might be given to you, or you'll have to remember it, and you can reverse FOIL it to well, not completely reverse FOIL it, but you can get this in your arsenal. So let's say we have the limit as x goes to 2 of 8 minus x cubed over 2 minus x. So you can see we can't use substitution here, but we can say that this is the limit. It's the same as the limit as x goes to 2 of, let's factor the top, that's 2 minus x, 4 plus 2x plus x squared all over 2 minus x. Now we get some cancellation, and now we can use substitution. Okay, so that's just an example of one that, it's another possible question. All right. Next one, number 5, find the points of discontinuity of the function, identify each type of discontinuity. This first one, we immediately look at the denominator and say, oh, we can't divide by 0, so x cannot equal 1. And so at x equals 1, what happens? Oops, let's go back to black. We have an asymptote, and as x, it's always going to stay, this function is always going to be above the x-axis because we're squaring the denominator and the numerator is positive. So as it gets closer and closer to x equals 1, it goes like this. And you can confirm that by thinking, well, just putting in 1.01, 1.001, 1.0001. The denominator is going to get infinitely small, so the function itself is going to get infinitely large, whether we go from the right or the left, and this is an infinite discontinuity at x equals 1. But what about this one? X over the absolute value of x. This is an awesome function because we have definitely a problem at x equals 0. But what about to the right when x is positive? When x is greater than 0, the function value is 1. Right? So think of a number like 4. We're taking 4 divided by the absolute value of 4, so that's 1. But when x is less than 0, so for example minus 4, we have negative 4 over the absolute value of negative 4, which is 4, so minus 1. So this is jump discontinuity at x equals 0. And remember, the other types of discontinuity are removable. So the term removable doesn't mean that it's called removable because the discontinuity can be removed by defining the function so that it's not, it is continuous. So this one up here, x squared minus 9 over x minus 3, once the x minus 3's cancel, this is really just going to look like a line with slope 1, intercept at 3, but there is going to be this hole right here at x equals 3.